Welcome to the Engine Performance Expo Live. I'm Ryan Thompson, the Applications Manager here at Rottler Manufacturing, and today we are diving in and continuing on a journey that's been going on for over 5 years. Community that's been created with the support of everyone out there watching. We appreciate that. To help the industry and really show the appreciations for engines and the industry as a whole. There's a wonderful community of individuals who have helped us out and are here today. And we're going to be discussing all aspects about engines, cylinder head porting, surface finish, metrology, balancing, and giving the appreciation and open discussion and dialogues that all of our people here today and many of us watching tend to have questions in any shop around America or around the world. And we're going to peel behind the curtain here and take a look at some of the conversations that industry leaders and experts have every day. Sitting beside me here in our first person is Darin Morgan of BES. Thanks for coming out.
Hey, you're welcome.
Yeah, how we doing?
Good, real good.
So you've been doing these wonderful educational seminars, and you came out and you said, you know, let's have a discussion.
Yeah, we started doing this when I was at Rare Morrison. I spent 26 years in pro stock engine development. And, you know, some of the baby boomers came in later. They raced back in the 60s and came back into it. But some of these high-speed NA engines, you know, they have maintenance. And we formulated a school to teach all of our customers not only to kind of appreciate all the work that we put into it, but how to maintenance. And that grew into the Rare Morrison Engine School. And pretty soon what we did was, we were doing this engine building school at every GM and Ford plant across the nation. And then I started the induction system, the Advanced Induction System training deal. And that was in 2000. And I've been doing it ever since. Just breaking down and telling people what I do for a living.
And what's been your journey? I mean, starting, how do you get you said the, you know, advanced injection, and how's it grown for you over your experience? I mean, you've been at it for a long time.
I'm going to kind of elaborate that a little bit on that in this presentation, but I was born into drag racing, but both my father and stepfather were drag racers, engine builders. My stepfather, Kip Martin, let me lay my hands on a pro stock engine when I was 20 years old, and from that point on, that was it. That's all I wanted to do. And I got into cylinder heads in a strange way because he had bought a flow bench and he spent the day on the flow bench and hated it and said, it's all yours. So I climbed on and never climbed off. But I learned very, very quickly that I didn't know what I was doing. Of course, you don't know what you don't know. The first time I ported a head, it lost 35 horsepower. But the flow went up. So I knew right then that. And then I got a mentor. His name was Harold Bettis from Superflow, vice president of Superflow for quarter of a century. And he took me aside and a couple of other guys who were still in the industry and gave us some education, told us where to go. He would never tell you what to do or what the answer was, but he'd tell you where to find it. And I'm going to talk about where I found it here a little bit today.
So that, you know, I've never hand ported heads. I've worked at Rottler for 8 years. And my experience with it is you have a CNC porting machine.
I have trained many people how to port cylinder heads. And it's one of those things that either you like it or you don't. Because, I mean, I can grind for 8 hours straight and just go through what we call the time warp that feels like 2 hours. And I grind manifolds all day long. I mean, it'd take me 10, 15 hours to do a manifold. Sometimes it'll take me 35, 40 because normally I'm taking a manifold and I'll show you some pictures here and sawing it into 4 pieces before I even touch it. And then I'll modify it, fabricate it, weld it, manipulate it into what I need, and then weld it back together, remachine it, and fit it to the engine.
And you touched on a good point. I mean, the first time I think anyone does in this, you get it wrong, and you don't really even know. I mean, if you just put the engine together and
porting's hard. Yeah, porting's hard work. It tears you up physically, and most people don't fight through the pain for that first 10 years to get your pain tolerance up till you can keep doing it. But you know, I turned 60, and I think it's starting to catch up to me a little bit.
Well, you know, so talking about it, and you know, airflow in general, and cylinder head port, it's one of those that it looks like black magic. like you said, you spend a lot of time in.
When I first started, it was black magic. You know, the people that I looked up to, Lee Shepard, you know, Dale Ike, Grumpy Jenkins, those guys, they wielded that black magic. Nobody knew what they were doing. Nobody. And nobody would talk about it. And it's like Harold Bettis said, nobody's going to teach you. You got to go teach yourself. And that's the way it was. And the reason I started the AAST was because that really angered me when I was younger, that nobody would tell me what the heck's going on, how this functions. Everybody would just say, CFM isn't all there is. Well, they wouldn't tell you anything else. So it looked like black magic, but it's not. It's STEM. It's science, technology, engineering, and math. That's all it is.
And that, so from my side, and you know, I like I told you, I'm really looking forward. I've never seen your presentations and all that, but I know they're great. You know, my background, mechanical engineering, take a couple aerodynamics courses, and you're looking at all those things, and I know that there is so much more than just CFM.
Because there are no college classes you can take to study an induction system of a high-speed racing engine.
Right.
There's nothing.
And it's, you know, so it's breaking that down. You have to get experiment. And I think, you know, in today's world, I look at it where you've got CNC, which you guys have a Rottler M69 HP.
Yeah, two of them.
And two of them, yeah. And you know, obviously those are a wonderful piece of technology.
They're awesome.
But if you don't know the fundamentals, and you haven't had that, would you say that
that is a wonderful Xerox machine that also gives us a lot of scientific information? Because on the Rottlers, I can print out the velocity profile of the entire intake tract with the splines. I know exactly how the airspeed changes through the system because of that. Before, what we had to do is take a port mold and slice it every quarter of an inch. And at Glidden's, we would have 30 seconds graph paper, and you would put that down and trace around that and then count the squares, and that's how you knew your cross-sectional area. So it took all day to get that. And I could walk up to a Rottler and get a printout and have it instantly.
How long would it take, you know, before the advent of CNC, and like you said, what you have and being able to create that? I mean, if you were...
Let's say to do a custom head, I would get the head straight from the foundry. So I would have a raw core, and then I would have to qualify that core, and then do test ports and everything else in it. It would usually take about 4.5 months to do a set of cylinder heads by hand. And now I can do it in 3 weeks.
So 4.5 months, and in that entire time, if you can't replicate quickly, I was saying, I mean...
Yeah, if you make a mistake, you're stuck with it.
You're just...
Yeah. If you got core shift on your qualifying and one wind stall, you just got to weld them all up and go. You're stuck. But on the next set, you can make that jog.
So I guess, you know, in just a different industry, right? But the advent of 3D printers and stuff like that, and these conversations, there's this, you know, rapid prototyping. And would you say that, you know, the technology today...
I will touch on that in this presentation.
Okay, wonderful.
Yeah.
Wonderful.
Yeah.
Well, let's get into it. I mean, you know, I want to hear from you and stuff. And for me, I'm not nearly the experience or the brains behind this that you got. I mean, I'm looking forward, but...
I have just been doing one thing for 40 years. And every waking moment of my life has been surrounded around this.
Yeah.
So I picked up some things along the way, and I'll pass them on.
I'm looking forward to it. Start from the top.
Harold Bettis once told me, if you want to learn about how to design an induction system and an engine, just study World War II. Those guys aren't doing anything different. They didn't do anything different than what we're doing now. We just have better metallurgy, material processing, and tools that they couldn't even dream of. Now, the aircraft you see right there, that was the R engine. That was the Rolls-Royce R engine. That was a predecessor to the Merlin. They didn't have fuel. Now, Doolittle in World War I dictated 101 octane fuel, which pretty much won us the war. The Germans didn't have it, so they couldn't produce the power we could. Now, this aircraft you see right there, that engine made 3,000 horsepower on the dyno in 1930. They had to back it down to 2,000 because it disintegrated. They didn't know how to build, you know, engineer. They didn't have a development program. That's what it is. Build it, break it, blow it, redesign it. And they didn't have fuel. They killed 2 guys mixing fuel to get enough octane. This is before TEL, tetraethyl lead. They had to they had the isooctanes and paraffins and everything else trying to get the knock sensitivity of that engine down. And they were pushing 50 pounds of boost to that thing. So the technology to do all the equations and formulas that I use are 50 to 80 years old. They were all developed back then, and in the 60s, it really exploded with the 4-valve, the Indy racing and stuff like that. And if you look at all the OEM engines you see now, all that is trickle down from racing, every bit of it. We're here to push the limits so they know the limits, the engineering. All the engineering that you do on rings and everything else that Total Seal does on rings, all that filters down into the OEMs. You know, people like me, I get up here and I talk about my specific job, which is induction research and development, cylinder head development, cylinder head design, cylinder head manufacture, and well as manifold design and manifold manufacture. I mean, after Pro Stock changed at Burr Morrison, they got into the Pro Mod stuff. I went to work for a company called Profiler because I simply wanted to learn how to make a cylinder head from the ground up. And that was a facility that gets the raw ingot of aluminum in the back door and ships the finished cylinder head out the front. Every process is under that roof, from mixing, degassing the metal, pouring it, making the molds, the tooling, heat treating, everything, machining right out the front door. So that was my opportunity. And I had been in Pro Stock for 24 years, but I wanted to design cylinder heads. So that's why I went to work there. And I designed about 80% of their product line. And I've never been afraid of, if I want to learn something, I'll just go do it. And I don't care what I'm paid. If I want to know that, I'm going to go do it. And it takes a team to build an engine. And you see people like me who get up and talk about what I do, my specialty, and a little more credit goes my way than really I deserve, because it takes a team to build an engine. I've never done anything on my own. It always takes a team, the engine builder, the CNC guy, the CAD, the finite element analysis, the CFD, computational fluid dynamics, and you rely on everybody and you work with everybody to build that engine design. So everybody has their specialty. Now this is our cylinder head row at BES, 2 Rottlers, an old 30 that we only use to do spring seats anymore. Now we have 4 head porters at BES. Each cylinder head porter is responsible for that cylinder head when it comes in the door and goes on the engine. Every aspect of it. Except usually welding. I'm usually the only one welding. But I do the same thing all day long. I don't do anything different than anybody else in this industry. I come in the shop, and these are the engine builders here, and we have 20 employees there at BES. And we are busy, busy, busy. We're always 8 months behind. And these engine builders, everybody works. This is Terrell. As a matter of fact, there's a video, I think, Rottler, that you did with Terrell. He's the machinist. He does all of our blocks, and another head porter, Mucker Hyde, and James. Everything that that cylinder head needs, that guy is responsible for. If it blows a rocker arm out and I weld it up, they remachine it and put it back together and put it out the door. Yeah, he's happy, isn't he? That's a cammer he's working on. A supercharged cammer for the street. I think it made about 1,000 horse or so. And this is our leader. This is Preston Mosier. He runs the cylinder head department there at BES and has for 15 years. And he knows what I know, does what I do. We have a great deal of mutual respect for each other. We work hand in hand all the time. And, you know, when you have a team, you have to have, you know, personalities that gel. And when they don't, you have to make it. Otherwise, it falls apart. Everybody at BES has, I worked there for almost 30 years, so it's stuck in my brain. We have a great deal of mutual respect for each other. We work really well together. This is our dear leader, Tony Bischoff. And he's on BES now since the 70s. This is what I do every day. This is my porting room. What I'm working on there, I don't just work on high-end NA stuff anymore, and that's one thing that's great about BES. I work on Mopars and Fords and Chevys and everything else. Anything that comes through the door, if you want more power, we'll do it. There I'm welding one of two sets of cylinder heads ever made for a Studebaker. Yeah, and the core shift was so bad they were unusable, so I had to machine out the whole short side deep into the cylinder head and weld the whole thing up and completely remachine it so we could use them. And then that's going in a museum. This is what I do, cut manifolds apart. And these manifolds, those manifolds were made for a specific purpose. And that's usually engines between 555, 600 cubes, 7,500, 8,000 and below, RPM. So 6,500 to 75, 7,800, that's their power band. But when I put them on a truck pull engine that has to turn 9,800, just hangs up there, I have to shorten all the runners, I have to increase the taper, I've got to raise the ports, I have to do everything because they don't make a manifold like that. They do now, but I'll get into that later. And that's what I do for a living, all day long, machine heads. And the manifolds and heads designed in the past won't work the best now, just like the ones that we do now wouldn't work then. Intended purpose dictates design. In other words, if you took a cylinder head, let's say a Pro Stock cylinder head from now back to the year 2000, it wouldn't run at all. Point in case, every year at Royal Morrison we build 2 engines. Pretty soon we had 13 engines in rotation and like 4 runners. And every 2 engines, we would make a design change. And we had noticed early on that as we rotated the valves, the natural VE curve of the engine moved up. And you see the rotation of the valves in some of these high-speed engines. The reason for that is, as you rotate those valves, it gives a straighter and straighter path out the engine. You can move more air through the engine, so it automatically wants to make its peak VE or peak torque higher in the engines, at a higher engine speed. But if you used one of those heads on a lower engine speed engine, it'd knock the wind out of it. It moves too much air. It'd be like putting too big a cam in it, too much duration, it'd knock the torque out of it. So over a period of 6 years, I took and went 5 degrees, 5 degrees, 5 degrees, and pretty soon, this is before the DRCE3, pretty soon the DRCE1 casting that Warren Johnson had made, my exhaust was into the valve cover rail, and I just went, okay, let's go for broke. And I did what is now referred to, very close to what is now referred to as the DRCE3 layout, which is a heavily rotated design. Half of the spring was out over the valve cover rail, and the whole side of the head was welded up, and you had to make custom valve covers to go around the springs. And that engine, we put it on the dyno, and it was a complete waste. It wouldn't make power anywhere. It was horrible. And we were shortening the runners and getting bigger core cams, trying to raise that engine speed. It wouldn't run at all. So 3 years later, we got 65 millimeter cores, you got 1-220 wheel guided lifters, you got all this valvetrain technology, steel rockers from Jessel coming into the mix, and we were able to control the valvetrain at higher engine speeds. And I grabbed those heads off the shelf, and they were the best heads we had, because everything else was tuned up around them. And nowadays, with these engines making an easy 2.8, 2.95 horsepower per cubic inch, it's either specifically designed for that purpose and does it, or it won't. You're at a point to where, you could tune the power curve on a 2 horsepower or 2.25 horsepower per cubic inch engine. It's a broad curve. You can be a little off on cam, a little off on induction signal, timing, whatever. It's not going to make a big change. You can live in that area. Your tuning window is pretty wide. When you get to 3 horsepower per cubic inch, it's a needle point, and you can fall off the edge. You could fall right back down to 2.8 really, really easy. So, 1 degree of timing could be 20 horsepower. And that's why you see in modern cars with unlimited NA engines like Pro Stock and Comp, you have a different timing curve and fuel curve for every single gear because the load changes.
Darin, how do you, tuning is a great topic. And, I'm 32 years old, and tuning cars, it's everybody, HP tuners, all this stuff's out there. Just quickly, what do you see on that compared to, what you're doing? And I like what you put, engines are a system, they're a dynamic system, and depending on what you're trying to optimize, you're playing, but you can't just look at one thing, and it's so easy as humans, I think
We're
always
trying
do
to tune a dynamic situation using static testing instruments, like a
Okay.
flow bench. That's a static testing instrument. We're trying to gain insight with that instrument and the data that it gives us into that dynamic event, that, like you said. And tuning, with the HB tuners, I took 3 years. Everybody told me I didn't know how to tune EFI, but I knew I needed to learn. And everybody told me, if you could tune an OEM, you could pretty much do it. So I got HP tuners, and I spent 3 years every single night tuning my street car, my Camaro, and just learning. And then pretty soon I was tuning 800 horsepower supercharged Camaros and Corvettes, and then I said, okay, I've got enough. I'm not a pro. I'm not proficient at it like the pros, but I know enough. I've gained enough insight that I can understand it now.
Do you
and
see
utilize it.
a point with that, and I think for a lot of young people such as myself, it's very easy, pretty low barrier to entry to get into tuning.
Yeah.
We would say, right?
Yeah.
And you want to make 700 horsepower, and I can probably figure this, and you've got a lot of smaller engines with turbos, and it's different. But where would you say, as a person getting into the industry, or someone who's looking at those things, or maybe does tuning is there a point where you say, like you said, I've learned enough, it's great to understand, but is there where you go maybe best time in porting?
You don't know what you don't know, and you never know enough. When people get into tuning, especially this younger generation, they are completely unaware of the actual dynamics that are involved in governing the systems that they're tuning. They're doing what works, just like we did. Try a port, lengthen the runner. I mean, I built 20 manifolds one year, just because we were tuning different tapers and lengths. And now I just use math and hit it within 100 RPM. I'm done. And then I can manipulate the taper a little bit, and I'm there. But it's experience, and experience is the best teacher, period. Because as you start experiencing this and start realizing, I don't know what I'm doing here, you go out and learn. You educate yourself, you come back, okay, you move on. That's why experience is the best teacher. When you have a lot of education and no experience, the application of that is lost to your perspective. When you're fresh out of college, both of my younger brothers are electrical engineers. They design circuits and for test equipment. Both of them are just completely brilliant. But when they both told me when they came out of college, they were completely ill-prepared. It took them 10 years to be able to become proficient at their chosen profession. And that's true. It's 10,000 hours. They've done many, many studies. It's 10,000 hours on every particular one. If you want to port cylinder heads, 10,000 hours, you'll be a pro at it.
That's the rule of 10,000 that gets come around, and I completely agree. I mean, I went through and got my bachelor's in mechanical engineering, and I never thought I would be an engineer. I just grew up working with things. Now my own father was a machinist at Boeing, and then a mechanical engineer for Boeing, and so on. But I kind of like you said, he was like, you got to be hands-on, because he was teaching engineers, and it is so easy. Going through the higher educational experience, I did, and it was wonderful. I really enjoyed it, and you learn a lot of fundamental theories and stuff. But you can get pigeonholed into that.
It's the application of that.
And it's great. I mean, I'm proud to be an engineer. I'm proud of where the mind had to be stressed, and the math and the firepower, and I recommend it to anyone who has the appetite for it, or at least trying it, with the grain of salt of, I was fortunate. I didn't go to college until I was 21 for that reason. I spent more time. I thought I was going to be an engine builder or start a shop or something, and then I thought, well, maybe I want to learn some of these other theories, and finally it sounds like a nice challenge, kind of like you go, actually I think I could learn that.
Nowadays you can teach yourself anything.
Well, YouTube, I mean it's the information age is
it's
insane.
Amazing. It really is. I mean, when I grew up, there was nothing. I had to drive to the local library. The Wichita State University's engineering library, I went there all the time, to look things up. And it wasn't very much help, I'll tell you. And now you can look up anything.
And I like what you said. So would you say, I mean, in cylinder head porting, or maybe if you're looking at tuning or getting into engines or something, I like what you said, go out and try. I have a young man who works for me, and that he was an electrical engineer, but he could, similar story to you. He's like, I've done one head, I ported it, and it was terrible, but I'm glad I did it.
Yeah.
So do you, I mean, is that to go buy some manifolds and heads and maybe just try? Or?
Every concept that I teach, and Tim Halstead and I, Drag Boss Garage, have a small channel. And it's a membership channel. It's $15 a month. And what that does is that little $15 a month hurdle, all that does is weed out everybody that just wants to watch it and critique, but the people that really want to know are going to jump that little hurdle. We got about 250 members, and I talk about this. And the feedback that I get from that is what drives me forward. Because when I teach a concept of seat-throat relationship to RPM and airspeed, and then people go out and do that, and it works for them, like in amazing ways, it's like, that not only over the years has verified my R&D, it's helped them out as well. And early on, no cylinder head guys talked to each other. Foltz, Bienemann, Keith Will, nobody talked to each other. Everything was a secret. I'd say the last 20 years that's changed radically. Because we all kind of know the same thing. And by comparing notes and talking to each other, we're verifying each other's R&D. We can move forward. It's like, I see this happening, this effect at this part in the fuel curve. It's like, do you see that with that? Yeah, I saw that. Okay, good. All right, let's go. Instead of sitting there wondering about it. Specific purpose, intended purpose dictates the design. When somebody comes in, for 26 years of my life, it was find power at any cost. And now I'm find power at this cost. So when a customer comes in, like Don Kennedy's Superstock Pontiac, he's been running that car for 30 some years. I've done like 4 sets of cylinder heads since 1990 for him. And I've seen the technology of a Superstock. Now, same valve size, same port volume, same everything. Now, how in the heck do you increase power on something that is port limited, valve limited, and everything like that? Well, the last time it was in, we gained 30. And I'll show you why we gained 30. But I used what I have learned in the last 10 years and put it into a Superstock engine. And that's what I never stop learning. And I learned that early on. When I was younger, I knew I didn't know what I didn't know. And it scared the hell out of me, because I was working on things that you should know what you're doing, So I never worried about sticking my neck out and failing, because that's part of it. A good engineer fails real well. That's why you build 22 manifolds and you run them across an engine. That's the old way. We used to call that the shotgun method. And Bob Glidden was really good at that. He'd try 10 things to your one, and hone in on something, and then exhaust that, and then go to something else. That doesn't work anymore. You can't do that anymore. Technology has reached a limit to where either you design it for that purpose and it does that, or you need to redesign it and make it work. And the shotgun method worked. You build 20 manifolds, like I said, and I've got pictures of them just stacked in the attic to hone in. And at the time, we were raising the engine speed. What had happened was Iaconio and Schmidt were using cylinder heads with a lower mean gas velocity, bigger ports, and moving the power band up as high as they could, and just dropping into a little less torque and slipping the clutch. So their tuning window is real narrow, but if they could slip the clutch right, they'd make a really good run. But if they fell off either side, they didn't have that torque and recoverability. We were tune the engine and the power band to the valve's efficiency curve. Make the most power you can in the curve where that engine is most efficient. Don't try to shove it up. So we had lots of torque, lots of recovery, lots of acceleration on the gear changes. The guys that use Schmidt motors couldn't use our engines because all their clutch technology and tuning was around the slip, and we didn't slip. Little things like that. So Iaconio's motors were picked up by Greg Anderson and Jason Line. Jason Line brought in the NASCAR technology where they were lofting the valve. Then he worked with Jessel. Well, they already had bigger ports at a mean gas velocity that was lower, ready to run higher. And then they threw those cams in there, and it's 100 horsepower and 1,000 RPM. And then everybody else, he left in the dust. And we were left to catch up. And that's why I built 20 manifolds, because we were trying to raise the engine speed. We didn't have the cam technology to do it. We caught up eventually.
Darin, what are you when you're doing 20 manifolds? I mean, what's the approach to? What were you changing? I mean, you had to be pretty structured.
Length,
otherwise
taper, plenum volume, and entrance. And the way when you're dealing with carburetors, you'd like to just stay in the port up, but you can't. You have to have that signal underneath the barrel. Well, you also have a short runner, which takes it away from the barrel. So then you have to play with your signal strength and your plenum volume and everything else and kind of arrive. It's like something like the plenum volume that you tune on the dyno will not work on the racetrack. It will not. Plenums are tuned on the racetrack because you can make the plenum as big as you want on the dyno. There's no dynamic load. But you're shifting gears and dropping RPM, and you stall that plenum, and it has no signal, and it leans out, and you can't accelerate. So that's something that's tuned on the racetrack. So everybody asks me, well, what's the perfect plenum volume? Whatever works. And I still say that to this day.
And that's where you
and
test.
There's like standard ratios. It's like it's relative to engine speed, just like taper is. You know, at 7,500, you'll have 30% taper, and by 10,000, you'll have 50%.
So when you're making your roadmap, I guess, to test, are you? I engineering school, it's, you can do incremental changes, or you can kind of do a boundary thing and go to one extreme, the other time. What's your approach in that
My
world?
approach is, for every change you make in an engine, you affect 5 others. I want to document those changes. So if I change a rudder length, its harmonic is supposed to go up 500, it goes up 300, and it leans out down low. What is that telling me it's doing? What does that engine want? The engine will always tell you what it wants. Always. So you have to pick up those trends. It's like doing the old days we used to do lash loops. It's like you'll have 20 lash on the intake, you take it down to 10, it picks up 10 horsepower. Well, it's telling you that you need more lift. More lift, less duration. Maybe a little tighter slope separation. See, it's pointing you in one of those 3 directions, so you order 3 cams with those changes and run them through the engine.
Gotcha.
Modifying manifolds is something that I really got into in truck and tractor pulling. And there is nothing harder in the world on an engine than truck and tractor pulling. Because these engines go up to 10,800 and stay there until that sled drags them down. So the induction system that you would tune for a truck and tractor pull is different than what you would do a drag race engine, what you would do with a road race engine, what you would do with a boat. Is that boat a prop boat or is it a jet boat? 2 completely different deals. There was a jet boat out there called Head Over Heels. Pro Stock Jet was the class. These guys were going out buying old Pro Stock engines. It was a jet boat. The jet's efficiency point was 8,000 RPM. Well, peak torque wasn't even at 8,000. These guys are going and spending $35,000, $40,000, $50,000 on Pro Stock engines. We just built him a spread port engine that made peak power at 8,100, and he dominated for 3 years and spent $50,000 less. Intended purpose dictates the design. So that's what I do. When somebody comes in with something, it's like, what are the load characteristics of this engine? What is the load curve? And you design for that. So manifolds, we didn't have 3D manifolds. We didn't have the prototype development that we have now. You had to take what was there and heavily modify it if you wanted to extract the power out of it. So what you're looking is the standard 454 Edelbrock 2916. It's been around forever. As a matter of fact, Lee Shepard was in on the design process with this with Vic Edelbrock. And I got to see some of the original plans. Then that manifold, we started getting bigger core cams. The engine speeds started going up, started building bigger engines with higher piston speeds, and it was choked off. It wouldn't work anymore. So we had to heavily modify the thing. So I would spend anywhere from $2,500 to $3,500 sawing, sectioning, fabricating, increasing taper, and doing all that stuff to this. So by the time you got this manifold back on the engine in order to turn 9,800 back then, you're going to spend about $4,500 on it. So when I went to work for Profiler, I said, enough of that. Let's design a manifold the way I would modify it for those engines. And then the Sniper, that's the Sniper manifold. And that was 30 horsepower more than the modified one, because I could do everything I couldn't do on the other one. And then over the years, engine speeds increased, cubic inches increased, valve lifts, piston speed, everything. So Edelbrock came out with the Super Victor, and that was another 20 horsepower. Well, what would happen if you took this Super Victor back 10 years earlier and put it on one of those engines that was turning 9,800? It'd knock the breath out of it. It wouldn't run at all. Because the volume, taper, length, everything this manifold is designed to do what it needs to with that engine combination. At that engine size, that engine speed, that piston speed, that valve size, that flow rate. Now here's three. All three manifolds are designed for their intended purpose. Now the Sniper manifolds still function great on like a 496 or a 545 that doesn't have to turn over 7,500. They're really, really good for that. But if you're going to turn higher than that, then you go to the Super Victor. Now, the Super Victor was designed to fit a broad range of engines. Because when you're developing a manifold for the aftermarket, you can't just have it one purpose. You know, you have to sell manifolds in order to make up for your R&D and development costs, your tooling costs, and everything else. So that manifold is designed to work from peak power 7,500 to 8,500. That's pretty broad. So it has a lot of taper and a lot of length. So it mellows out. If you're on lower RPM, it will mellow the torque out. If you're in a higher RPM, it'll actually nose the top end power up. So it's not fit for a specific purpose, it's a broad purpose. This is the original Dart manifold. It cost $3,500 to cut this in half, section it, refabricate it, weld it, remachine in 2000, and it added 30 horsepower to the spread port engines that we were building at the time. Because when this originally came out, 7,000 RPM, for Dart spread port cylinder heads on a 565, 600 cubic inch motor, 7,500. That's about it. And then you had Top Sportsman come in. Well, you're going to turn them up, 8,000, 8,500. Well, they were totally ill-equipped for that. And they also had a horrible, what we call split harmonic. The outer runners are 1.4 inches longer than the inners. That's a 1,400 RPM spread in tuning between those runners. And just like the Sniper, the one thing I tried to do, there was a 1,200 RPM split on the harmonics with the original Edelbrock, and on the Sniper I got it down to 400 RPM. So it tunes up, it compacts that VE curve and makes more power throughout the entire curve. Now that was worth 30 horsepower by the time I sawed that one up. So when I was at Profile, I said, let's do a manifold better than that. And this took the harmonic split down from 14 to about 1,900. I mean, it wasn't perfect. You look at the manifolds today, I'll show you one of the newest, the brand new 3D printed from Chris Arachico. This thing is over the top. Absolutely specifically designed to fit that engine, and the way it responded was unbelievable. Now, when you have a manifolding, camming, I always call it the natural VE curve. You have this many cubic inches with this much valve cam lift. It's that natural VE curve. That engine is going to want to tune up with that cam and those piston speeds and engine speeds at, say, it's going to want to make power at 9,000. It's my job to develop the cylinder heads and manifold to do that, to operate that engine in its natural VE curve where it's most efficient. Now, modifying this one costs the customer $3,000, or yeah, they used to cost $3,000 and 30. Now we got 40 horsepower. Saved them $3,000. You could go buy this, bolt it on, port match it, and go. But there are so many different engine combinations now, varying, so many different motorsports disciplines, whether it's truck and tractor pull or boats or what have you. The manifolds like this, 10 years later when Edelbrock came out with this was much better than the Hitman, because by that time We're making 700 cubic inch motors turning 8,500 RPM. We have a large volume engine, super high piston speeds, engine speeds that, you never want to turn a 700 cubic inch motor, but we're doing it. Because now we have 60 millimeter cams and we can lift the valve 1/100. And by the way, Unlimited Extreme Pro Stock, the gross valve lift's about 1,350. And nowadays with a 75 millimeter cam, which I'll show you, in comp motors turning 10.5, 11,000, we can have 1/100 gross lift easily with 272 degrees of duration. And that's one thing we did notice with the larger core cams. And it took 1 to 2 years. Every time that core size grew, you can't just take that lobe and just grow it. Doesn't work. The kinematic motion is completely different. Every time we went up in lift, we went down in duration. If you look at the 54 millimeter, to turn 9,000, you'd have 286. And then the 55 was 282. And then the 60 was 278. The 65 was 276. And the 75 millimeter is 272. So what you're doing is you're putting the valve into a higher lift range and a higher flow zone at maximum piston speed. But you're also getting a smooth, perfect draw relative to that piston drop. I'll expand on that here in a little bit later. With the rapid advancement of cylinder heads, camshaft, valvetrain, making a cast manifold for racing is no longer cost effective. The amount of effort, time, and money that you have to put into a manifold to modify it, you couldn't get there from here. You just couldn't do it. And you got 40,000 in tooling to make the first 20 manifolds. You got to sell 200 before you break even. You're not going to do that on specialized engines. Before we had to rely on the aftermarket grew out of Pro Stock and Comp and a development of the late 80s, and then Dart in early 90s and Brodix. All those cylinder heads came out of racing, and now the R&D, the development that's going on is moving at such a rapid pace that we can't wait for the aftermarket. We just got to do it ourselves. Just make it out of billet. And we have the technology to do that. I mean, I have 500-600 bore space truck pull my engines in the shop. I mean, whatever you want, we can make it anymore. So the 3D printed cores. Now, the manifolds themselves are not 3D printed, but the sand cores are 3D printed. And you don't have to put up with all the problems of the tooling. You have to have draft. Like that spider core, when you have to pull it, you have to make allowances to pull that core out of that mold. So you have to have negative draft. Well, if your runner's like this, how are you going to pull that? You can't. So now you're at the limit of the tooling. And with 3D printing stuff, we have no limits. You don't have to have the draft and all the other things. And like cylinder heads, the water jacket core and these modern cylinder heads are all 3D printed cores because you can't get the water flow through a cylinder head with a standard core pull. It's impossible.
This is the first I've really heard of this. I mean, the 3D printed cores, they're printing the core and then they're actually using that. They're
pouring in the mold, yeah.
What's that machine look like? I mean,
it's like a standard 3D printer.
Huh.
Yeah, it prints the sand core itself. Put the cope and drag together, put the spider core in, pour the aluminum, boom, you got a manifold.
Wow. And you're right. I mean, the benefits of it.
And once you have your basic CAD drawing, your 3D image, you can manipulate that.
Right.
So if it's, hey, listen, I got this 6, I know you built that for the 565 turning 9, I got a 632, it's going to turn 10 too. I need more taper, I need this, okay, boom, I get a manifold.
And where are the people making, so I mean, there's clearly manufacturers or people working around. I mean, it's
Profilers 3D printing.
Okay.
Yeah.
So that's pretty, and that's the way now, and it's pretty accessible, you would say, and it's giving you
that is the way everything will go.
Because certainly, I mean, 3D printing the shapes, you're growing parts. That's always been the benefit, and finding these different applications.
Pretty soon you will be actually printing them out of. I mean, they can print in stainless steel.
Titanium.
They can print in any titanium, anything. Yeah. It's just those processes are extremely time-consuming and expensive right now. When the cost per unit comes down, we'll utilize it too.
Right.
It would cost, if you're going to spend $4,500 on a manifold that's designed for its exact intended purpose, or you're going to spend $4,500 or more to modify something to try to make it work on that, well, that's a no-brainer. This is a raw 3D printed core. Now what this was a test manifold, and you can see the flanges. This manifold weighed 51 pounds. It's absolutely monstrous. This is right out of the core with the gating cut off. And this is the way I get manifolds, all my manifolds. Because I want to set height, I want to do everything that I can. Well, I had to put this on an engine that had to turn higher RPM than its design criteria was actually, from what it was designed around. So I had to do something I've never done before, but I thought it was so cool, I'm going to show you. I had to mill the flanges all the way down. I had to take 750 thousandths off of those flanges. Now I do this on a vertical mill, high speed. I have special fly cutters that I've made. I could just wind them up and send them, and they'll take off 100 thousandths. And my speed and feed is the drop on the gear on the motor. If the motor drops, I'll slow it down. But if you grind your tooling properly, it'll send it right through. So it took 8 hours just to mill this thing and get it just cut and set and do the bolt pattern in the top and cut it out for the carb. And I set it on there, and the runners were still 375 too long. That's 400 RPM. I can't take that hit. I need to tune this engine exactly where its VE curve is. So I cut the whole bottom out. Now this is a very thick manifold. And the thickness, can you see my cursor? Okay. The thickness of this wall right here was 650 thousandths thick. So I set up and I milled it internally and took 375 off inside. So that's what it looked like after I'd milled the inside. And then I ported it, radiused it, and welded the floor back in. And it tuned up perfectly. Now he can use that data from me machining that manifold to make alterations to his 3D model. And the next manifold that comes out will be exactly what I need.
Wow.
This is the new Big Hulk manifold that Chris Arachico did. This thing has everything right. And I'll point out the things that it has right that other manifolds don't. The plenum volume ratio to cubic inches and engine speed. As the engine speed increases, you have to have more volume in your plenum. That's a given. But you also have to tune that plenum volume to be reactive on the gear change. If it's a 5-speed. If it's a 4-speed, it'll be a little bigger. If it's an automatic, it would be real small because the gear drop is bigger. So that's why I say you tune plenum volumes on the racetrack. And if I had to tune that plenum volume, what would I do? How would I do that? I would saw the top off and make a spacer and bolt it up. Fab it. But this thing hit every single aspect. You can see the runners are leaned in. They're not bent. Let me say that again. They are not bent. You do not bend runners under any circumstance. Period. Anytime you bend a runner anywhere, efficiency drops. Carrying the fuel around that corner is a nightmare. And the bigger the bend, after you get it about 20 degrees, VE is going to take a nosedive. You want the ram effect. You want to take every bit of energy you have and aim it at that valve. And you'll notice all these high-end 3D printed cores are coming out. They're straight, straight, straight. And usually they'll go straight, and I use like a 2-inch radius right here at the base. Makes one turn, if it has to. And most of these ports that we deal with have a lot of what we call guide offset. They are offset to the guide center line. The opening of the port, the guide's here, it has to move over for the push rod. And you have to make allowances in the port design for that. And I'll show you that later. But this is one that I put fuel injection nozzles, nitrous nozzles, fuel rails, and everything else. And when I got done with it, as you see here, every runner is the proper size. It has the perfect taper. It has a perfect harmonic length. It has what most manifolds don't. It is so important, runner isolation. You see there's no common walls in this manifold anywhere. You'll split your harmonic when you do that. People come out of the outside runner and they continue that wall out. Well, that pulse is going to come out and grab that wall and move around. It's going to make that runner an inch longer. If you blow it out, boom, you shear it. And as you shear that energy, when you have a positive pulse, come out and you shear it clean in the plenum, the refraction wave is of a higher amplitude. If you have this huge radius or this big wall coming out, that energy is dissipated into the plenum, so the incoming wave is of a lower amplitude, decreasing VE, and splitting the harmonic, which spreads the power band out, lowers peak power. So this is what we can do with 3D manifolds. We can get perfect runner isolation. You notice they're all together. This is a single 4-barrel manifold. There's just enough runner isolation between them to where they don't interact that much, unless you want interaction, which is another deal. Cylinder head design has changed a lot. And we have all the pro stock technology of the early to mid 2000s coming into the aftermarket now, heavily rotated valves, because we have larger engines operating at higher engine and piston speeds now, so we can utilize that. 75 millimeter cam cores, we're able to control the valve train like never before. Before we had the larger core cams and the better roller diameters and Billy Godbolt in his little lab working away on kinematic motion, we were brutalizing the valve train on pro motors, comp motors. Anything that had to turn high engine speeds, we were literally just opening it as fast as we could to get the valve into a higher flow area at 76 degrees after TDC, the highest piston depression, the highest piston speed area. So if you could lift the valve 900 and you put a faster ramp rate cam in there and got it to 1 inch, you had 25 more CFM at the maximum piston speed, maximum depression, and you could see power from that, but you couldn't control it. At some point in the engine speed range, it would go really chaotic. And at one point in pro stock, there was teams with huge slide hammers just to bust the keepers loose. Every round you'd have to change springs, every single round. And they would slam to the seat so hard that it would gall and lock the locks and the retainer together. You could not break them loose without a sledgehammer. That's how much we were brutalizing it. And then they came out with these cams. And now not only can they control the valve motion, but they can control the valve motion relative to piston. Because when that piston drops, that valve has to chase it. But what we were doing is we were blowing past the part that controls. Now it's a controlled depression. You have a constant draw on it. Instead of blowing through and trying to get that valve to a higher flow area and missing the draw for the first 20%, now they can time it. So you have this constant draw, so your signal is so much better, so much smoother, so much controllable. And that has changed port development and manifold development. Now, we used to use huge bowls. Dale Ike used to do his Pontiac heads. You could stick your fist in that bowl with room to spare. And we used to call that charging the bowl, because when you have a positive harmonic coming in and you have a high pressure area sitting over the valve, that charges that bowl up. So when that valve opens, boom, you get a hit. We got the hit because we were blowing the valve through the depression zone where it could get a draw. That was a makeup. So now we don't have to do that as much. Still have to do a little bit, but not near as much. This is a 75 millimeter core. I'm going to show you the engine. It's a JC51 Ford that I designed the cylinder heads with Ford. And for 2 years, every week we drive up to Michigan and set with Mose Nolan, if you know who that is. I was so very lucky to get to work with him. He was on, if you watch Ford versus Ferrari, Mose Nolan was the head of the development for those 427 engines. And this is a 75 millimeter core. You could easily put a 650 lobe on this and control it to 10,000. This is, he's running like 1/8 rockers on this, so this is like a 620 lobe. What's strange is we have so much control. Billy and some of the camshaft and lobe designers have so much control over this. It's gotten to the point where, oh man, I only have 1/8.5 rocker arm ratios. Well, before you had to go down in rocker arm ratio to mellow everything out to get the engine speed up. You have to do that. They could just design a lobe to fit those rockers. That's where it's become. Now that 75 millimeter, that's 2.95 inches, and you got 2.4 on a main. So the cam is now much bigger than the main. And then you have 1-220 wheel-guided lifters. So what you've done here is you've changed the relationship of the base circle to the roller. You can't have this huge base circle and this tiny little roller. Think about the relationship, gear ratio, and roller speed, action. So now you need a bigger roller with the bigger cores. Now that slows everything down. Now you have total control over the acceleration. No more super asymmetric ramps slamming things open. Now, where did this come from? Where did the wheel-guided lifter? It was first used at Wright Aircraft Company. All radial engines have had it for 80 years. Again, we can't think or invent anything that has already been invented. Our job is to perfect it with modern technology. Now today, if I want a custom valve train, I will show you the port from this cylinder head. This is a Ford SC2 cylinder head modified to work on an LS engine. He's shooting for 12,000 RPM with this at 355 cubic inches. So the whole valve train had to be custom made. The ports had to be offset differently to fit that LS architecture and the valve train. So Preston here has made the 3D printed base, and he will sit there and make different bases and modify it, trying to get the push rod and the rocker arm and the lifter as much in plane as possible. You know, the old spread ports, you'd have a rocker arm like this, and then the push rod's like this, and the rocker's like this. Well, as it opens, it's opening away. So on one of them, you'd lose 35 thousandths lift just because of the motion off to the side. So you get everything dead straight, and in plane with each other to capture every bit of lift you possibly can. And you don't want any motion but to have that thing move that valve open. If it jigs or jogs in any one way, that can instill harmonics in the system. You want everything dead straight. And I can show you a video here later of a video from Dr. Andy Randolph at Hendrix that he sent me of the NASCAR pushrod just sitting there, just jelly. Talk about camshaft and valve train development. When NASCAR went to the better cams and lifters, they saw power, but they saw some problems with the fuel curve. It put a hole in the middle of the fuel curve. The fuel curve would go up and it would dip, and the power along with it. It's like, what is that? It would come right in and out. Well, the push rods at that time were such that they flexed. So all their R&D, all their camshaft lobe development valve train was around the fact that that push rod was doing this and storing energy, so later in the cycle it was releasing it into the rocker arm. And what that did is the push rod had a harmonic that upset the valve train and dipped the fuel curve is what it was. So then they got their hands on tool steel tapered push rods and knocked 12 horsepower the average right out of the engine because all their lobe development was around the fact that push rod was doing this. And when they made it stiff, it changed everything. Intended purpose dictates design. This is the JC51 500 cubic inch pro stock cylinder head that I designed for Ford. This was my baby, and nobody used it. They were trying to go Hemis because they were raising the engine speed at that time, and they made a Ford Hemi. And I was done with this cylinder head at Ford, putting the finish in. It already went to the foundry, and Larry Morgan said, well, all my R&D is around the Hemi. Can you make a Hemi head? And I understood where he was coming from, totally. You know, I mean, he was going to have to start over. Little did he know it was a huge mistake. And little did I know it was a huge mistake. This thing is effortless 2.9 horsepower per cubic inch. We put it, Clinton F., who races A Econo Dragster, which is one carburetor with a wet sump oil pan. He asked me, he said, would this engine, would this be good for comp? And I told him, it will annihilate them. They won't even know what hit them. And he said, good. And he went out and bought every single piece in the United States. And he's built 3 engines. And first shot on the dyno, 2.82 horsepower per cubic inch. First pull. 1,400 horse out of 499.8 cubic inches with one carburetor and a wet sump. And it'll easily turn 10.5, never hurt a thing, all day long. The valve train is stable. This engine is designed. He is not operating the engine where it's designed to operate. This engine is designed to operate from 94 to 11.1. That is its operational natural VE curve. He's operating it up to 10.5. He has another 500 to 600 RPM left if he can feed it with a single carburetor. That's the trick. The carburetor has become a limiting factor. You'll notice the runner length on that? Very, very short. Now, how are you going to have a port that comes out and all of a sudden, boom, has this big runner on there? You're not. That's why when you look at Pro Stock ports, they look huge. They're shrinking down. I'll show you some ports here later. They're flared. Half of the runner is in the head. That's why they look so bad, so big. This went out, ran faster than any gas dragster, any AED has ever run by a long shot. I think the record was 206, he went 215. And he went, I think the record was 660, 642 is what he can run. And he's been #1 qualifier and won 3 races with it. And he's building a couple of others, one of them 2 carbs on gas for a dragster, which will, that motor will make 1450 real easy.